Have you ever really wondered what's going on inside an AI's mind? Forget all the sci-fi stuff for a sec. Today, we're going to be engineers and artists, and we're going to build an artificial intelligence brain right from the ground up, piece by piece. You ready? Let's jump in. So here's our game plan. We're going to start with the absolute basics of logic, then build the actual structure, teach it how to learn on its own, give it the gift of language, and then we'll look at the real art of putting it all together.
All right, first things first. A real brain can't just see the world in black and white, right? So step one for our AI brain is to give it the ability to understand all those shades of gray in between.
I mean, think about it for a second. A classic computer, it runs on a super simple principle. Something's either on or off, true or false, a 1 or a 0. But how in the world do you define a word like tall or warm? Where does kinda tall stop and tall begin? This is a massive roadblock for traditional computer logic.
And this is our solution. We move from classic logic to what's called fuzzy logic. See, classic logic lives by this rule called the law of the excluded middle, which is just a really fancy way of saying there is no middle ground. You're either in or you're out. But fuzzy logic, it just throws that rule right out the window. It allows a statement to be, say, 70% true and 30% false.
So how does it pull that off? With this clever little thing called a membership grade. Instead of a hard yes or no, we just assign a value somewhere between 0 and 1. So a person isn't just tall or not tall, they could have a 0.8 membership in the set of tall people. You see, this one simple idea is an absolute game changer. It lets us build logic on top of all that real-world nuance.
And you can even start to build rules with these grades. A system could be designed so that, okay, if you're a 0.5 in the tall category, maybe that translates to a 0.25 in the very tall category. And just like that, nuance is possible. Our AI brain can finally handle ambiguity.
Okay, so we've got the logic system down. Fantastic. But now we need an architecture to actually run it on. It's time to build the structure of our brain, the artificial neurons and synapses that make up a neural network.
You know, at the very heart of every single artificial neuron is basically a switch. It's called an activation function. It takes in all these signals, and then it has to decide, should this neuron fire and pass the message along or not? There are a few key types, but let's just look at a couple of the most common ones.
So check these two out. Sigmoid spits out a value between 0 and 1, which is kind of like a probability, right? But tanh, which is really just a scaled-up version of sigmoid, it outputs between -1 and +1, and that makes its output 0-centric. That little difference can actually help the whole network learn faster and more efficiently sometimes.
So what's the big deal here? What's the takeaway? Well, a single neuron on its own is just a simple little switch. But when you start connecting them and stacking them into layers, something incredible happens. All of a sudden, this network can solve unbelievably complex problems, like the classic exclusive OR puzzle, which is literally impossible for just one neuron. That layering, that's what gives our AI brain its real power and depth.
We've got a structure now, but an empty brain is pretty useless, right? So how does it learn? We're not going to sit it down with a textbook. Nope. We're going to let it learn from pure experience.
Now, one way to teach an AI is called supervised learning. And with that, you have to feed it a massive answer key, tons of correct input and output pairs. But with reinforcement learning, there's no teacher. The AI, we call it the agent, it just learns by doing. Exactly like how you'd learn to ride a bike. You try, you fall down, you adjust, and you try again.
And here's the beautiful loop that drives the whole thing. The agent takes an action, the environment gives it feedback, maybe a positive reward for a good move, a negative one for a bad one, and then the agent updates its internal strategy. It has one single goal: get the most rewards possible over time. It's this simple, powerful cycle of trial, feedback, and improvement.
And does it actually work? Oh yeah, T.D. Gammon used this exact process to become a superhuman backgammon player. And of course, more famously, AlphaGo used reinforcement learning to totally master the incredibly complex game of Go, beating the very best human players in the world. This is learning on a completely different level.
Okay, so our AI brain can learn tasks now, but it can't communicate with us. For that, we need to build its language center. This whole field is known as natural language processing, or NLP for short.
The very first step to understanding language is to figure out how to turn words into numbers. And we do that with something called word embeddings. The best way to think about it is like this. We're giving every single word a set of coordinates on a giant map of meaning. So words like king and queen would end up really close together, but words like king and, say, cabbage would be miles apart.
So why do we even need to do this? Well, because the older ways of doing it, like something called one-hot encoding, were just clunky. They created these gigantic, mostly empty spreadsheets of data. That's what high dimensionality and sparsity mean. And worse, they had no way of knowing that words like dog and puppy were related. There was just zero shared information. Word embeddings solve all of those problems.
And over the years, we've developed some really powerful models to create these embeddings. Word2Vec is one of the big ones. Glove takes a totally different approach based on counting words. And then you have something like EALMO, which was a huge leap forward because it realized that a word like bank can have different meanings, right? A river bank, a money bank, and EALMO actually gives it different representations depending on the context. Super clever.
And the practical uses for this are just everywhere. Once we build this language center, our AI can do things like perform sentiment analysis on product reviews, understand the actual meaning of an entire document, or even look at a photograph and generate a caption for it. This is the crucial bridge between human language and machine understanding.
So, let's take stock. We have logic, we have a structure, we have a learning mechanism, and we have a language center. Now it's time for the final, crucial step, actually assembling our intelligent system.
And here's the big secret. You'd think building these things is all just hardcore math and code. But as this quote says, there is a real art to it. Deciding how many layers you need, which of those switches, those activation functions, will work best, how to wire it all up. It takes a ton of intuition and creativity.
You'll also find that the most powerful systems out there today, they aren't purists, they're hybrids. They combine that fuzzy logic we talked about with neural networks and other techniques, all under this umbrella called soft computing. Basically, they take the best tool from each toolkit to build something way more powerful than any one piece could be on its own.
Which really brings us to our final thought here. We've built this brain piece by piece, blending science with a surprising amount of artistry. But that just begs a much bigger question. If we are the artists, what kind of intelligence are we trying to create? And what will it, in turn, create for us? Now that is something to think about.